I have installed this one, so I can comment them, but you may have to install. Are you installing? What else? So either do them one by one or do all of them together. It's the same thing. So we are using the packages in 8 to 18. So because I have installed them already, I just loaded them. But if you have not, you can install them. So you just need to make sure that all the packages in line 8 to 18 are inside 5 and 6. So cars,
Okay.
then TS, then ECN, UC8. I think they are all there. Parallel is in base R, so we don't have to install that. Line 17. So let's see if you can get to where, yeah, if you're able to run, let's say, first Diebold Yilmaz, then we can attempt to interpret and continue tomorrow. So the last package, the read Excel, remember previously we were reading the CSV. Sometimes always trying to convert your data to CSV may be stressful. So lately I use read underscore Excel, and this package is the one that does it. That helps you to do that. So if you use the read underscore Excel function, your file can be in any of the Excel extension. As long as it is not CSV, you should be able to load. So we load that one, and we can actually attach. We didn't attach, maybe it's not necessary. But what you should note is the dimension is 10 columns because we need that. Okay, that's fine. So this is actually African stock market indices.
Mm.
As you remember, once you load data in Excel, it comes in R, it's a data frame, but we want it to be a T series or time series to be able to work with. So we use the TS function in line 36 to change it. But here, if you look at the data, we have date column. We don't need the date column for now. If you look at the head, the date is there. So I'll just ignore the date column. Start from column 2. Okay, so this is the data. Now you can see that the class is now a matrix or an array. And it's also TS. That's the one we need. And we have to remember this is VAR. This is VAR, vector autoregression, to start with. So we need to form a VAR model. To form a VAR, your question is how many lags do you need to use? So we can look for the lag by using the lag select function. Usually lag 1 should be fine, but you can just confirm it. So if you look at this, we need to look at the lag selection here. If you are modeling, you always will gravitate towards the model of the least number of parameters, and that will be 1. So according to the Schwartz information criterion, we use lag 1. If you are using 7 lags, nobody is interested. So lag 1 is fine. So with that, we can now form the lag model, and we indicate P equal to 1 as our lag. So we can run that model, the VAR model. And we can just look at it. We don't need it. We only use it to do the next analysis. So you can just look at it, and this is, you can save it even to look at, you can look at the plots. It's in different plots. So for each of the variables, we have 10 variables. So if we zoom in, so this is DCI. Margins too large. My screen is not big for this. Okay, we don't need this plot anyway. Okay, so here we want our processing to be fast. So normally you have a lot of variables, so you don't want to sit there waiting for the estimation to finish. So you can try to speed it up with this one, the make cluster. 8 is the number of calls I want to use. If I have up to 8 to work, I don't have up to 8 calls, to use the maximum that we can. So if that something is happening. Okay. Hit to see next plot. So we didn't finish looking at the plots, that's why. So we are done with the plots. The screens, they are too big for my screen. We can solve that one later. But we don't need those plots. Okay. So now that we have set our VAR model, we can estimate our connectedness now. So this function will do the Diebold and Yilmaz 2009. And realize that var.4t is our VAR model here. And forecast the Diebold Yilmaz, if your data is large enough, 100 is the best forecast horizon. If it's 80 works, but if it's getting smaller and smaller, your results are not usually nice. And this function is to check whether you want to set the off-diagonal correlations or values to be 0 or not. Obviously, we don't want to do that, so we put false there. If you run line 60, depending on the speed of your PC, may take long or short. This says return graphic state. Have I loaded the packages though? I think I did. So let me check again what may be happening. Yeah, here. Okay, maybe earlier I had not loaded the packages. So it is done, and you can see. Okay, so this is what is going to happen. In terms of the tables and the plots especially, we will not use the plots from here. We'll use the plots from TVP bar because the plots inside here are not nice. So when I did my work, I took the output and I plotted them manually with other codes, which you don't need. But when we go and use the connectedness approach, the plots there are nice, so we use them there. Okay, so based on the Diebold Yilmaz connectedness index, so this is basically impulse response. How do we know that this is impulse response? Because we have to and from. This go up a bit, so we have two. So let's look at this plot. Let's look at one after the other. So look at the diagonals.
Yeah.
99, 99.7. See, those are the largest numbers there.
Yeah.
That's very instructive because look at this as a variance covariance matrix. So the variances are on the diagonals.
Yeah.
They are usually the big ones. If you look at them as correlations, they would have been 1, 1, 1, but they are not correlations. They are, because this is a VAR model. So this is the connectedness between the variable and itself.
Yeah.
At time t minus 1 and at time t. And they will usually be the biggest numbers. So we are not interested in that anyway. What we are interested in is the differences. So if you take BRVM and This is Botswana. BRVM and Botswana, for example, that's you can multiply all of these by 100 to make it more interpretable. So this is 12%.
Yeah.
So from you see, this is from BRVM to Botswana. Now, if I go to BRVM column and I see BRVM here, okay, we are BRVM and Botswana. Where is it? Go all the way to. Okay, so let's look at BRVM Botswana. That's 12%, and we go across. So if you look at BRVM here, this 12%, look at to and from. So go all the way across to the last column here, from. And the question is from where? From where? So it is from all the other variables in the system to BRVM. That's 6%. So, sorry, BSC. So BSC, from all the other variables to BSC. Now, if we come down, DSC down, let's go down to DSC 2. Where is it? So that's the first part. So that's 0.05. Take note of that number, and later when we do net, we should see the difference. So the difference is 0.01, right? So to all the other variables from DSC is 5%. And from all the other variables to DSC is 6%. That means DSC is transmitting more than it is receiving. So it is a net transmitter, if you look at it. So because they are transmitting, BSC transmits 6%, it is receiving 5%. Okay. Now let's choose a random one. Let's say South Africa, JSC. From JSC is 0.56. Yeah, and 2 is what? Is 2
is 0.13%.
Yes, it's 0.31.
So if you check the row, the 2 row.
Yeah, 2 row on FTSE is 3.1.
Yes, 3.1.
And from is 5.6. Which is not very surprising, is it? Well, this is South Africa.
Yeah.
Yeah, it's not surprising.
So from what percentage will you classify it as being significant? Or it's based on the average of what you see within the matrix or the table?
So by significant, you mean in terms of quantity or probability significance?
Yeah. So if I'm doing a bivariate analysis, or I'm taking each market and I say this is a net transmitter, this is a net recipient, but the difference might be just small, 0.1, 0.2, 0.3. At what point would you say the transmission is significant enough?
In the literature, it is not being talked about.
Mm-hmm.
There are no thresholds for this. Later, if we are doing network plots, for example, and you want to combine all the averages and the totals, because you are doing a network, you are looking at all the connections. You may want to minimize smaller connections, so you can set a threshold and cut them out.
Yeah.
But if you are doing bivariate, for example, you are interested in which one is a net transmitter or a net recipient. In terms of the magnitude, it's not really, that's not the focus of discussion. I haven't seen the focus of discussion in the literature, unless you are comparing different, say, net transmitters. So maybe South Africa is a net transmitter and Nigeria is also a net transmitter. I want to know which one of them is stronger.
Yeah.
I think I did that even in my work. I was comparing the other emerging markets against the US, which is a stronger market. So it's not really about the size. It's whether there's a net recipient or transmitter.
So the from is the shocks it receives from others.
No,
Is it?
it is what it is giving out. So from BSC, so from BSC, so
Oh,
BSC,
rather,
the
so from, okay,
from you and to you.
okay.
So it's a little bit confusing because
Yeah,
from is going to be to others and to is going to be from others. So you have to pick out the others part. Okay. So, but you can also pick out even the bidirectional from here. Because if you look at BSC to BRVM is 0.21, right? And BSC to BRVM is 0.12. So from BSC is 2.21 and sorry. So from BSC to BRVM is 0.21, but from BRVM to DSC is 0.12. That gives you the bidirectional net. And you realize that here, DSC is a net transmitter. True or false?
BSC.
Yes.
You are
BSC is a
comparing,
net transmitter.
you are comparing BSC to, okay,
And BRVM.
BRVM. So 0.21.
And 1.2.
Yeah.
Yes, you just need to take your time a bit because from BSC to BRVM is 0.21.
Yes.
And from BRVM to DSC is 0.12.
1.2. Yeah.
So that makes BSC a net transmitter
Yeah.
and BRVM a net recipient of the same magnitude. So if you take a random one like GSC, so from GSC is 0.03 to BRVM, for example. Okay, let's choose another one. So GSC to say Egypt EG X30. So from Ghana to Egypt is 9%. And then from Egypt to Ghana is going to be
that's
0.05. Realize that Egypt is a net recipient from Ghana. So Ghana to Egypt is 9%, Egypt to Ghana is 5%. So Ghana becomes a net recipient. But even if this one is not clear, we are going to do by pairwise. That one will bring them out quickly. Later, we will see the total connectedness. So normally, when we go ahead, we will see another column or another row that gives us a TCI here, and we even have a net. So the net will be the net for, you see the 0.06 from BSC and to BSC. There will be a net that will be written down as the next row. And there will be a total connectedness. So the total connectedness will be all the off-diagonal connectedness in the system. So then you know, is the system really strongly connected or loosely connected, just as you may find in integration analysis. Okay, so this table is not complete, you can say that. So that's what the Diebold and Yilmaz 2009 gives you. What we can do is just change this to, let's run the 2012 and see. So you see this one is 2012. If we run that, you should have another table like that. So almost the same. These ones seem to be bigger in terms of magnitude than the 2009. But that's not our focus. I can just comment that and leave it. So you realize that now you can have your from and your to and your net, and we have the overall and we have the pairwise. Let's just go through them quickly and we can do something else. So we can just get only the from. Of course, that will come from the other table. So this is from BSC, from BRVM, from Egypt, from Ghana, then there's Nigeria. This is Nairobi, This is Rwanda, South Africa, and Dar es Salaam is Tanzania. So these are what they are sending out from them. And you can see the 2 as well. Where is 2? Yes. Okay, I didn't print out 2. So let me just put the from there and print out the 2 as well so that we can compare. So this is 2. So from BSC and to BSC. So the 2 is to the whole system, to all the variables. And this is from all the variables. So you realize that 0.59, 0.059, and 0.050, realize that BSC is a net transmitter to the whole system. If you come to BRVM, BRVM is a net recipient from the whole system, which is not very good. This is basically about 10 stock markets. So BRVM will be a net recipient. Egypt will be a net recipient as well. Ghana will be a net recipient. Nigeria will be a net recipient. Nairobi, net transmitter. Then we go to this Rwanda, 0.02 and 0.023. So 0.029, 0.02, so net transmitter. South Africa, net transmitter. And Tanzania is also a net transmitter. So this is net transmitter to the whole system. Okay. And we can print the net themselves. We don't have to spend time checking them. I need to change this one to DY09, not BK11. Change this. DY09. So the net. So these are the nets. So the negatives are the nets, positives are the transmitters. So the negatives are recipients, positives are transmitters. And they should correspond to how we interpreted the ones above. If it doesn't correspond, it means that we turn them upside down. There's one we call overall. So overall connectedness in the system. So we can see that one. Where's the output one? So 1.547%. So that's not a lot. So this is what in subsequent tables you will see that as TCI, even CTCI, that's corrected connectedness. We'll differentiate between them when we get there. Now, the pairwise will take all the pairs. So this is 10 variables. So we're going to have like 45 pairs. So that's what the pairwise will do. So that you know you can compare the markets against each other. So if you look at, so the first one is the from, and the second one will be to. So this is BSC to BRVM, and it's positive. It means that BSC is a net transmitter. And again, it is net here, but here it is, it is still a transmitter here, but between Ghana is a net recipient. Nigeria, still a transmitter, but Nairobi is a recipient. It comes to Rwanda, it's a transmitter. So you can make all the comparison. And you can do this in frequency domain. So this is static. You can look at this as time domain, but you don't really want to say time domain. We just say static. If you move it into frequencies, then it becomes frequency domain. So all of these can be done in frequency domain. So that's basically for the Diebold and Yilmaz.